The big question for this segment is, does chemistry represent a new level of complexity? The universe, with its infinite complexity, is the way it is because of chemistry. The energy we derive from the sun, the photosynthetic reaction center of plants, the genetic material that is passed between generations, and the way we see and hear, our sense of smell and touch, our ability to speak, to think and dream. Our existence is the result of chemistry. Like all scientists, chemists aim to understand and make sense of the complexity. To do this, we make observations, propose explanations for those observations, which is known as proposing an hypothesis, and then we devise experiments to test those hypotheses. Chemistry is a huge field because there are a lot of questions to be answered, many concepts to be explored, and there's also an enormous scope for creativity within the discipline. It could be said that while we study complexity associated with chemistry, as chemists we also generate new complexity through synthesis, which is the making of new compounds. The world of chemistry in the 21st century is a result of hundreds of years of acquired knowledge, of thought, of experimental design, of testing hypotheses, of interpreting results, of predicting outcomes and testing those predictions, of formulating new theories and advancing our understanding. As students of chemistry today, we truly stand on the shoulders of intellectual giants. If after that, the thought of studying chemistry sounds daunting, it should not be. The expression says the longest journey starts with the first step, and for a chemist, that first step is understanding the building blocks of matter, and they are the elements. An element is composed of its constituent atoms. For me, as an organic chemist, the model of an atom consisting of a nucleus composed of positively charged protons and neutral neutrons, or just a proton in the case of a hydrogen nucleus, surrounded by orbiting electrons is as much detail as I need, with the added notion of the electrons orbiting at different levels, also known as shells, also known as orbits, around that nucleus, like the planets orbit around the sun. The number of protons in the nucleus of an atom determines which element we're dealing with and is known as the atomic number. In some cases, the atoms of a given element may have a different number of neutrons in their nucleus. Such atoms are known as isotopes of one another. The sum of the number of protons and neutrons in the nucleus gives us the atomic mass. So isotopes of a given element will have the same atomic number, but a different atomic mass. Dmitri Mendeleev is credited as the father of what we know today as the periodic table of the elements. In the table, the name of the elements are shortened to atomic symbols, a 1 or 2 letter abbreviation. Example, C for carbon. These abbreviations might not always make sense to us, but that's because they're often derived from the Latin version of the name. For example, capital P little b for lead comes from plumbum in Latin. As the name, the periodic table of the elements suggests, this is a table that lists the elements in terms of their related chemical behaviour. That Mendeleev realised was repeated periodically, which means in a regular manner. At the time, in the 1860s, only 60 elements were known, but now we have over 100. Mendeleev wrote out the then known properties of the elements on cards, and when he laid these out on a table in order of increasing atomic mass, remember at this point there was no notion of protons, neutrons or electrons, he noted that the elements with a given property regularly occurred in the same relative order. For example, a very reactive non-metal was followed by a very reactive metal, and then with a less reactive metal. This is shown in the figure here, taken from an article written by Mendeleev in 1869. For example, Cl, chlorine, K, potassium, and Ca, calcium, or going from Br, bromine, Rb, rubidium, Sr, strontium. The remarkable power of Mendeleev's system is that made him aware of inconsistencies which were later proven to be the result of incorrect atomic mass determinations, which were made by other researchers. So some of the data he was working with was wrong, and he predicted that was the case. He also correctly predicted the existence of missing, i.e. unknown at the time, elements. The periodic table makes sense of complexity. In the modern version of the periodic table, the elements are arranged from left to right in order of increasing atomic number in what's called rows. And as we move from the top to the bottom for a given column, Each element has the same outer shell electron configuration, with the electrons one shell or orbit further out from the nucleus as we go down a column. So, on the left-hand side of the periodic table and through the middle, we have metals. A typical property associated with such elements is they conduct electricity, they're shiny, and they're metallic in appearance. As we move to the right, we transition into elements with non-metallic character. To very briefly illustrate the power of this way of arranging and ordering the elements, we can look towards the extremities of the periodic table, the columns to the far left and the far right. In terms of the number of electrons in the outermost shell, at the far left of the modern periodic table, we have the alkali earth metals, also known as Group 1. All of these metals are extremely reactive. They have only one electron in their outermost shell. They react violently with water and produce hydrogen gas. They readily lose one electron and form ions, known as cations, with a charge of +1. Just to step back for a moment, ions are electrically charged species and a cation has a positive charge. The next column is known as the alkaline metals, also known as Group 2. All of these elements have 2 electrons in the outermost shell. They're also reactive, but not as reactive as the alkali metals in Group 1. These elements lose 2 electrons to form cations with a charge of +2. Let's skip across to the far right. This column contains the noble gases. It's also known as Group 8. This collection of elements is essentially inert, which means they are unreactive. They have a full outer shell of electrons and do not form ions. Taking a step back to the left, we hit Group 7. These are the halogens. Elements in this column all have 7 electrons in their outer shell. They readily gain 1 electron and become ions, in this case anions, which are negatively charged ions with a charge of -1. Taking another step back to the left, we hit Group 6. Elements in this column all have 6 electrons in their outer shell. They all readily gain 2 electrons and become anions with a charge of -2. We can use this information to predict what happens if any element from Group 1 is combined with any element from Group 7. We will have a +1 cation combined with a -1 anion to form a salt with an overall charge of 0. Examples include sodium chloride, NaCl, which is table salt, lithium bromide, LiBr, or potassium iodide, Ki. If a Group 1 element is combined with a Group 6 element, we will have a +1 cation combining with a -2 anion. To get a neutral salt, we will need twice as many +1 cations to neutralize the -2 charged anion. So the formula would be Li2 for lithium oxide, Na2 for sodium sulfide, for example. The subscripted 2 tells us there are 2 lots of the element immediately before it. So Li2O is made up of 2 Li pluses and 1 O2 minus. If a Group 2 element is combined with a Group 7 element, we will have a +2 cation combined with a -1 anion. To get a neutral salt, we will need twice as many -1 anions to neutralize the +2 charged cation. So the formula would be CaF2 for calcium fluoride, or BaI2 for barium iodide, for example. How about a Group 2 combining with a Group 6? So a +2 cation combining with a -2 anion. So the predicted formula for magnesium, Mg2+, combining with oxygen, O2-, is MgO, correct. What about barium, Ba, combining with sulfur, S? BaS is correct. There you go, you're on your way. Order from complexity encoded in the periodic table. Thank you, Mr. Mendeleev.